So let's continue going. And so there's kind of a problem session associated with this, uh, where I just like to work through a few more examples of how this method can be used in ways with, I don't know, various levels of perhaps cleverness uh, to actually say some really interesting things. And Shaheen, before the break, asked something about the crossing number of a graph and whether this business could be used at all to understand the crossing number. And actually, it just happens to turn out that one of my it wasn't something that I was going to do here, but one of, I think, the most beautiful probabilistic proofs that I know actually involves exactly this, the crossing number of a graph. So recall that the crossing number of G, this is the minimum number of crossings of a drawing of G in the plane. And the question I'd like to think about is to estimate the crossing number of G. So I'm given a graph, and I'd like to say something like intelligent about this crossing number. And the first thing that you might be able to say is, okay, so if G is planar, then Euler's formula says I can't have too many edges. Implies that the number of edges in G is at most, I'm going to write here 3n. You can do a little bit better, right? A 3n minus 6 or something like this. But nonetheless, what I've written is true. And this gives a bound on the crossing number already, that the crossing number of any graph G, it gives a lower bound, is at least the number of edges of that graph minus 3n. And again, I could subtract 3n minus 6, but this is good enough for what I want to do. Why is this true? Well, I start with kind of a maximum planar subgraph of G that has at most 3n edges. And now every single other edge that I add to this creates at least one crossing. So hopefully this makes sense. And what I want to show you is a very simple way of estimating, of amplifying this to get what's known as the crossing number inequality. So I'm going to consider an induced subgraph of G, where I pick each vertex, let's call it H, And I'm going to pick each vertex to be in H with probability probability P. All right. Now, it's still true that the crossing number of H is at most however many edges are in H minus however many vertices are in H, 3 times however many vertices are in H. So this crossing number inequality that I get from Euler's formula still holds. And now what I'm going to do is I'm going to take the expectation of everything. So I'm going to consider the average, right? So this means that the expected crossing number of H is bigger than or equal to the expected number of edges of H minus 3 times minus 3 times n of H. Right? H is random. I have two numerical quantities. One is this crossing number of H. It's always bigger than this quantity on the right-hand side, and therefore the average of these values has the same inequality. Now, I can actually understand one side of this really precisely. So the easiest to understand part is just the number of vertices I get. Like, what are the number of vertices? Well, I'm picking them with probability P. So I'm going to get at the end a P fraction of the vertices. That makes sense. Good, hopefully. Yeah. How about edges? Well, here, in order for an edge to survive this process, in order for an edge from my original graph to be an H, both of the endpoints would need to be an H. So actually, what I get here is the expected number of edges of H. For each edge, the probability that it survives this random process is actually P squared times, and this is true for all the edges in the original graph. So there's a kind of nonlinearity that's happening here that I'm taking advantage of. Okay. Now, what's happening with the crossing number itself? That's like a much more complicated thing. Actually, finding the crossing number of a graph, this is hard, serious business. However, if I think of a drawing of G originally, and I just restrict H to have exactly the same drawing, then many crossings are going to disappear. And in particular, the only way that a crossing in my original drawing would survive is if all 4 of these endpoints survive. So in the original drawing of G, I just consider that I look at the same layout for H. What I get is actually P to the 4th times the original number of crossings. The only way a crossing will survive is if all 4 endpoints corresponding to those edges survive. And in an optimal crossing, in an optimal drawing, the only crossings will be on edges from disjoint endpoints. And now maybe I could do better than that, but this is an upper bound for the crossing number of the expected crossing number of H. So perhaps this random H that I have picked has a smaller crossing number, but this turns out to be an upper bound. So now what I have is I have an inequality that looks like the crossing number of G is at least the number of edges of G over P squared minus 3 times n, the number of vertices of G, divided by P cubed. And now what I can do, I mean, this is something that is true for any P less than 1. So let's go on for a second here. So I have this inequality that the crossing number of any graph G is at least, I'm just copying it so that I remember, the number of edges of G over P squared minus 3 times the number of vertices of G over P cubed for any P in 0, 1. So now I should just try and pick a P that makes this as large as possible. And that will give me a better and better upper bound. So if the number of edges of G is at least 4 times n, just a little bit bigger than 3 times n, I can take this P to be like, I'm going to take it to be 4n over the number of edges. This is less than 1. And this gives me a result. It says the crossing number of G is at least, again, here I'm going to get the number of edges of G cubed over, I'm dividing by P squared. So here I get 16n squared minus, on the other hand, I'm dividing this by n cubed. So when I do this, I'm going to get 3 number of edges of G cubed over, now I'm going to get 4 cubed. 4 cubed is 64, right? N squared. And this is the number of edges of G cubed over 64n squared. So I took this bound. I started with a bound that was kind of linear in the number of edges. And this probabilistic trick amplified it into a bound that actually grows like the number of edges cubed over n squared. And essentially up to this constant 64 and up to this restriction that the number of edges of G is at least 4n, this is best possible. So this gives actually the proper kind of rough scale behavior on this crossing number. So again, it's just an example of how I can use these ideas to understand things. So did that make sense, Shaheen? This was your question. Yeah. So again, these kind of ideas, what I really want you to see here is that they're really broadly applicable. So next, let me do something that Mafunda mentioned to me in chat. That wasn't part of my original plan for this session, and I didn't actually add it very quickly between sessions like I did with this. So let me move over here, and I want to prove the following proposition, that almost every graph has diameter 2. Actually, we were inches away from proving this in the main session, but then I ran out of time or something. It took a little bit too long. So let me prove this. Let's think about this. So what does it mean that a graph has diameter 2? That's really the same as saying that if I take any two vertices in the graph, x and y, then they should either be adjacent or they should have a common neighbor. So all pairs adjacent or have common neighbor. Okay. So suppose I live in the world of G n 1/2. So I'm going to flip a coin, fair coin, for every edge. And I either take it or not. Remember that this is a uniform distribution on graphs. All right. And I fix an x and a y. And I ask, what is the expected number of common neighbors? I'd like to prove that it's very likely that the diameter is 1/2. So I'd like to say that hopefully I fix this x and y, they should have at least some common neighbors. But actually much more than this is true. So what's the probability? This is the audience participation portion of the talk, by the way, so feel free to unmute yourself or answer in chat or whatever. So I look at one of these, there are n-1 other vertices. What's the probability that both x and y are adjacent to them? So the probability that x is adjacent to them is 1/2. So Shiheen said 1/2, but I need both x and y, so I need 2 coin flips to be heads in order for them to be common neighbors of x and y. Did that make sense? So in order for them to be common neighbors, I need to have gotten heads twice. So actually the probability isn't 1/2, but rather 1/4. Did that make sense? Yes. So this edge has probability 1/2. This edge has probability 1/2. Aha. So I expect actually like n/4. Technically it's m-2/4 common neighbors. Well, that's actually a lot. That's a lot of common neighbors I expect. The probability that the number of common neighbors differs from this expectation by more than lambda. Okay. Well, now I think about this. This is actually, for each of these, it's independent. Like the edges involved for each of these vertices down the line, these are all independent random variables. So this Chernoff bound that I mentioned applies. So this is less than e to the minus lambda squared, whatever, over twice the expectation minus lambda over 3. Okay. Now, of course, this is just for one pair. In order to say my diameter is 2, I would like there to be common neighbors between every single pair of vertices. So the probability that there exists an x and y such that this number of common neighbors differs from its expectation by more than lambda. Well, this is less than how many pairs are there? They're like n choose 2 pairs. I'm going to be lazy and just write n squared here. That's still an upper bound for n choose 2. E to the minus lambda squared over twice the expectation minus lambda over 3. And if I pick a lambda that is big enough so that this probability goes to 0, then actually what I've said is that with very high probability, all pairs of vertices will have so many common neighbors. It will be close to their expectation. And if I take this lambda to be like some constant, 10, don't take 10 too seriously. What's more important is this root n log n. What this root n log n will do is cancel this expectation, cancel this constant 2 here, and just give me some large constant times log n here. That'll beat out this n squared. This implies that this probability goes to 0. Aha. So what I've now done is I've seen that not only is almost every graph have a diameter 2, but actually in almost every graph, nearly every pair of vertices has lots and lots and lots of common neighbors. Nearly n over 4 common neighbors. And in particular, not only my diameter 2, but there are lots and lots and lots of paths of length 2 between every pair of vertices. Does that make some sense, Mafunda? This is your question. So, it's a lot to digest in a short amount of time, I know.
Well, can I ask you a question?
Yeah.
And do you need this inequality? Because you could compute the probability that the distance between x and y is more than 2.
That's true. I could have been a little bit cheaper about it, right?
It's just 3/4, right? 3/4. So the probability that for any given potential neighbor.
That's right. So I could have been a bit cheaper here if I just cared about diameter 2. I showed here actually that there are lots and lots of paths. So I showed that there are lots and lots of paths. Of length 2. I think what Mario is mentioning is if I really just wanted to show that there's at least one path, so the probability that there exists at least one path between x and y is what? Well, path of length 2. For each of these, there's a 1/4 chance of being a path, and therefore a 3/4 length of not being a path, but they're all independent. So I could have written this, if I just care about the existence of a single path, then this probability is like 1 minus 3/4 to the n minus 2. So the probability that there does not exist a path is actually extremely small. 3/4 to the n minus 2. I mean, this is really, really tiny.
Right.
And therefore, the probability that there's some x and y so that there's no path is like n squared times this, which is still really, really tiny.
So how does this compare with what you got?
So how does it compare in which way? So what I showed here was actually almost all pairs of vertices have like n over 4 common neighbors. And therefore, there are many, many, many paths of length 2 between all of them with high probability. And this other proof shows that with even higher probability, there's at least one path. In that sense, they're incomparable, right? They're saying different things. Now, they're both proving kind of the same result in the sense that almost every graph has diameter 2. One is proving, I guess, exactly that. The other is proving even more structure and not just diameter 2, but I have many, many, many paths between them. Depending on what it is you're actually doing with this, one or the others of these might be more useful. There's actually like a really interesting theory of what are known as quasi-random graphs that says, actually, if you have a graph that has this property, that almost all pairs of vertices have very close to n over 4 common neighbors, and you have about n squared over 4 edges, then you have all sorts of properties that random graphs have. For instance, in a random graph, you can count any graph that you want. You can count how many copies of the Peterson graph are in a random graph. You can compute the expectation, and then it's a little bit tricky to show, but it's like close to the expectation. And already these two properties, that you have the right number of edges and the right number of common neighbors that we just showed here, is enough to imply results on all of these things. That actually, if you construct a deterministic sequence of graphs with this property, then you get all these properties of random graphs for free. But on the other hand, yeah, so this is another nice way of showing just this diameter 2.
Right. Yeah.
I kind of wanted to do a little more practice with the concentration inequalities, so I was taking this as a thing.
Thank you.
Yeah, please. I already scared off, I guess, many people in the first part. So if you've got various questions, you can feel free to just shout them out, and I'm happy to try and answer them. We'll work through a few more things. I'll try and show you a couple other cool tricks. I wanted to look originally, so when I was kind of coming up with problems, I wanted to say something about independent sets in graphs. So, of course, so of course, finding the largest independent set and set in G, this is MP hard. But on the other hand, one of the kind of really beautiful inequalities that one can get, a lower bound on the independence number of a graph, a very beautiful way of proving it is using this probabilistic method. So kind of wanted to show it off. This is known as the Caro-Ray bound. So for any graph G, the independence number of G is at least as big as I add up over all the vertices, the degree of V plus 1. So this gives a lower bound on the independence number of any graph, based just on the degree sequence of the graph. And if I think about the convexity, if I just try and estimate this, okay, I can relate this to the average degree. So the independence number of G is always at least 1 over the average degree plus 1. This actually follows from Turan's theorem. And in fact, this bound that I'm going to show you can be used to derive Turan's theorem. So it's another good example of how taking a random set and computing expectation can give me a good bound on graph parameters. Now, as I kind of alluded to during the main portion of the talk, if I just like pick vertices at random in my graph, well, if that p is with some probability p, if that p is small, I'm not that likely to, I don't pick out very much. And if that p is large, I'm not that likely to pick an independent set. And so just picking vertices blindly in my graph isn't that smart. And in particular, I know that for an independent set, like smaller degree vertices are likely a little bit better to have in my independent set and so on. So there is some logic in trying to be a little bit smarter. But anyway, there's a very nice proof of this bound that goes as follows. So I'm going to pick a random ordering of my vertices. So I'm going to order my vertices as V1, V2 through Vn. I'm just going to pick the order uniformly at random. There are n factorial possible orderings. I just pick one. And I'm going to take a set X so that V is in X if it is the first vertex in its neighborhood. In the ordering. All right. So if I think about a vertex, it's got some neighbors. In my graph somewhere. And again, I'm now going to flop down an ordering on my graph where maybe this is vertex 3 and this is vertex 5 and this is vertex 10 and this is vertex 8 and this is vertex 1 and this is vertex 7. It's a big graph, right? This is a big part of a small part of a bigger graph. And I look at this and I'm going to take this V to be an X if it's the smallest, if it's the first thing. So for instance, if vertex 1 was one of its neighbors, I would not take this V. But if this was 17 instead, then 3 is smaller than all of its neighbors, and I would take it. And the point of this is, first off, that this X is an independent set. Because I'll never pick both a vertex and its neighbor to be in X, because, well, I can't have both of them be the smallest. One of these vertices comes earlier in the ordering than the other. One of these two. And they can't both be the smallest in their neighborhood. So I'll never pick two adjacent vertices by this method. And the other thing that's true is that the probability that V is in X, well, on this neighborhood, all orderings are equally likely. So what's the probability that this V is the smallest? Well, any of these vertices are equally likely to be the smallest in the neighborhood. So this is 1 over the degree of V plus 1. And now that means that if I compute the expected size of X, this is just the sum of these 1 over the degree of V plus 1. Aha. But that means that there is an independent set that's at least that large. And this turns out to be occasionally tight. It's tight if and only if I'm the disjoint union of cliques. Otherwise, I can squeeze a little bit more in here. But this is another example of a proof where I can take a random process, I can understand an average in this random process, and it gives me some bound on something in the graph. And something I really wanted to highlight was that often it's not the results that are that interesting, but rather the methods. So an independent set is a subgraph of maximum. Here I mean induced degree. So an independent set is a subgraph with the maximum induced degree of 0. What if I want a subgraph on my graph that the maximum induced degree is k? All right. Well, I can take the same approach, actually. I can just take this idea and I can recycle it. So if I want an independent set, what I did was I took the smallest vertex in my ordering. So I took a vertex, I always took X to be the smallest, the vertices that were the smallest in their neighborhood. What if instead I take a random ordering and I take V and X if it is one of the smallest K plus 1 in the ordering. In its neighborhood. Again, in the neighborhood. Well, sorry, I don't even mean maximum degree. Actually, I can't bound maximum degree this way. So let me say subgraphs with no complete graph on K vertices, K plus 1 vertices. Okay. So it's not maximum degree, it's actually degeneracy in some sense. But I want to think about subgraphs with no complete graph on K plus 1 vertices. So an independent set is a subgraph with no K2. What if I want a subgraph with no triangles, or a subgraph with no complete graph on 4 vertices? Then what I can do is what I suggest here. I take this random ordering, I take a vertex if it's one of the smallest in my neighborhood. I can't have a K K plus 1 because sorry, because one of these vertices, if these are all connected, these are all complete. One of these would have to be the biggest in this random ordering, and it will be bigger than these K other vertices in its ordering. So if I take this vertex to be in my set, if it's one of the smallest K, then actually instead of an independent set, what I get is a graph with no complete graph on K plus 1 vertices. The probability that V is in X is now like K over the degree of V plus 1. I need to be like a little bit careful here because, I mean, this could be bigger than 1. So really what I get here is the minimum of these two things. If my degree is small enough, I will always be one of the smallest K in my neighborhood. But otherwise, this probability will be less than 1. And the same result, the same proof, proves the following proposition. So every graph G contains a k sub k plus 1 free subgraph on now I take this minimum of k degree of v plus 1 vertices. The result is, of course, a little bit different, but the proof idea is exactly the same. The wonderful thing about the probabilistic method, and maybe, of course, I could talk about other problems, but maybe now is a good time to just kind of wrap up and let people ask any questions if they have them. But one of the wonderful things about this method is it gives ideas and it gives techniques that can be used in many, many ways. And they can be modified and that can really be used to, again, address lots and lots and lots of interesting problems. So this has been, just the briefest of taste of what is a huge subject. And I hope that people at least got something interesting out of it and learned something. And yeah, so thank you for all of you who have stuck around for the very end. I could keep on going for an entire semester, of course, but yeah. So Shaheen asked, the probabilistic method used to find families of graphs with certain properties, and it certainly is. So, for instance, quite famously, Erdős used the probabilistic method to find graphs with large girth and large chromatic number. How do you do that? No, it's perfect. It's perfect. So how would you do that, by the way? Well, you can take a random graph and you need to pick the p like a little bit carefully. But if p is not too large, then I don't expect too many short cycles. Maybe there are some triangles. Maybe there's some short cycles around. And on the other hand, I don't expect too large of an independent set because the edges are kind of strewn around randomly. And what Erdős showed to prove this was just that actually what you can do is you can take a random graph and you can just delete some vertices from short cycles. That doesn't increase the independence number of the graph because I'm just deleting vertices, not edges, but it does make my girth large. And if you juggle the parameters right, then what you get graphs with no large independent set. That means that they have pretty large chromatic number and they have no short cycles. And graphs with many, many properties have been constructed randomly. So there was an old conjecture of Hajos. It's too early in the morning here to pronounce Hungarian names, so I apologize. That if you had chromatic number at least k, then you can, if you had chromatic number t, then you contained a kt subdivision. And actually, random graphs disprove this quite easily, that you can construct graphs, you can understand the chromatic numbers of these graphs, but in some sense, there's not enough room for a subdivision of these graphs. So the probabilistic method is used all the time. Random graphs are used all the time to construct graphs with with lots and lots and lots of nice properties. All right. Any other last questions? So the idea used to show that almost all graphs have diameter 2, can something similar be done for average distance? Sure. And in lots of regimes. So of course, if you just take a graph at random, it has diameter 2. I kind of know how many pairs are at diameter 1 or at distance 1, because that's the number of edges. But the same ideas that went into especially this proof, that the diameter is 2, where I look at neighborhoods. Now I can think of, instead of taking this to be 1/2, I take this to be some p. Okay. Now, instead of this being m minus 2, I get something like p squared times m. So I can look at the same problem with different levels of sparsity. And I can already see from this that if p is something a bit bigger than 1 over the square root of n, 1 over the square root of n is when this gets small. So this gets small when p is much less than 1 over the square root of n-ish. And it's big if p is much bigger than the 1 over the square root of n. So actually, even on fairly sparse random graphs, where p is like 1 over the square root of n, you get you still have diameter 2. So even like fairly sparse random graphs have diameter 2. And then you can think, well, what if I'm a little bit smaller than 1 over the square root of n? Then I go through these phases of diameter 2, diameter 3, diameter 4. And even if I take p to be very small, I can still understand the diameter and distances in random graphs very well. So random graphs have really a kind of small world phenomenon. If I have a random graph that's connected, its diameter is quite small. Introductory books, yeah. So if you're interested in the probabilistic method in general, there's a book of Noga Alan and Joel Spencer, just called The Probabilistic Method, that does an amazing job of presenting a lot of stuff from this subject. It kind of ramps up in difficulty pretty quickly, but it's a really good book that I like a lot. If you're interested in random graphs in particular, there are several books. I don't think any one book is quite perfect, but there's a book of Lucic, Kuransky, and Rushinsky that's quite good, just called Random Graphs. There's another book of Alan Fries and Rushinsky on random graphs, or not Rushinsky, Kuransky. Various combinations of Polish people that I need to get right. That's also pretty good. There's another book, if you're interested in graph coloring, there's a very nice book by Malloy and Reed called Graph Coloring in the Probabilistic Method, that shows how all of these ideas can be built up to solve various graph coloring problems. So for instance, one thing that we're probably all familiar with is if you have a graph whose the maximum degree is D, then a greedy coloring will color it with D+1 colors. So the chromatic number of any D regular graph, say, is at most D+1. And in this book of Muller and Reed, they show how different techniques can be used to improve this if I have a little bit more. So for instance, if I have a triangle free graph, I can color graphs in D over log of D colors. And they use these kind of theorems to illustrate a lot of probabilistic methods. It's a really nice book. Anything else? All right, I think people are done. That's good. All right, thank you all for sticking around to the very end here.